Chapter 9 is combinations of functions, and today we're going to talk about sums and differences of functions. Realistically, we see more combinations of functions than we do single functions. So realistically, for example, as a swing moves back and forth, it's going to slow down over time. What we've been doing with the sinusoidal function implies that it is constant and continuous at the same rate of change, rate of increase and decrease and all that. It's consistent all the time, but that's not realistic. A swing would not do that. It's going to slow down. So we need to start changing our functions a little bit. The four graphs below model the combinations of functions. Which graphs match which equation? So what do you think? So if we were in class, of course, I would take some votes and everybody would take a guess. Now you have no idea. You've never put a log function together with an absolute value. We've done a little bit with this kind of thing with sine and cos, but in terms of putting two linear and reciprocal function or exponential, we haven't put them together before. So these are just guesses right now. This is just an educated guess. So take an educated guess on where you think, which graph you think matches each equation. Let's start with equation A. Which of the four graphs do you think is the same as equation A? Well, the only one that, you don't really know, but the only one that looks kind of loggish, the right answer is graph 3. What about equation B? Which one do you think equation B matches? So a sine minus a cos, it could be really 1 or 2, right? They both look sinusoidal. It's actually 1. And equation C is x minus 1 over x. So there's definitely restriction on that one. That looks, maybe that one's a little more obvious that would be the fourth one because of the way that one looks. That leaves us with the second one for equation D. Again, I wouldn't have expected you to know that. We're just starting off with a guess. So we're going to do some examples, and when we do, you might need, if you're using my handout, you will be crowded. You probably need your own piece of paper, but we'll see how it goes. Review from grade 11. Oops, that's not supposed to be there in the bottom. We've got f plus g at x equals f at x plus g at x. That's just notation. So if you see the notation that looks like this, it's the same as this. And this is we're a little more comfortable with that, right? F at x plus g at x. Same thing when you're subtracting. You can put them together or you can separate them. So that was grade 11. You may not remember that, but that's why we're reviewing it. We've got a function f here and a function g, and we want to determine f at plus g at 4. So remember what I just said, f plus g like this at 4. This part here, let's rewrite it like this. I think most of us are probably a little more comfortable with it looking like that. So I'm going to put f at 4 plus g at 4. That's maybe a little clearer. So what is f at 4? So here's my f function here. F at 4 means I'm looking for the x value of 4. That's there. So f at 4 is 1 plus, what's g at 4? Look to the g function here. When we have g at 4, that's the x value is what's inside the bracket. When do we have an x value of 4? Right here. So g at 4 is equal to 2. 1 plus 2, of course, is 3. So f plus g at 4 is 3. Next one, g minus f at 2. Well, that's the same as g at 2. Subtract f at 2. What is g at 2? So you're looking for x value. These are x values in the brackets, right? Just up here. These are x's. So g at 2, here's the 2. So g at 2 is 4 minus f at 2. Where's f at 2? Here it is. F at 2 is 3. So that's 1. So that's all there is really to basic adding and subtracting when you're given the coordinates. But you must have matching x values. If I asked you for f plus g at, let's say 1, that would be f at 1 plus g at 1. Well, I don't have an f at 1. I have g at 1, that's 5. I can't add these two. So the x values must exist in both functions. or we're not able to add them. We'll talk about, that's the domain issue. We're going to talk about that in a minute. The domain of f plus g or f minus g is the intersection of the domains of f plus g. And I know you did Venn diagrams, probably in elementary school. So if this were an f and this were a g here, we have to only have the overlap, the intersection. F plus g and f minus g are only defined where the domains of both f and g overlap. So if this is my whole f function here, and this is my whole g function here, we have this problem up here. If one is in the domain of G, but it's not in A, then it's not an overlap piece. So your domain has to have matching X values. So now we finally catch up to this little piece here that's been sitting there. We're going to state the domain of f plus g at x, given f at x equals 2 to the power of x, and g at x is 3 over x minus 4. Let's start with the domain. Let's just look at f at x first. Let's find the domain of f at x. Let's do that first. What's the domain of f at x? So here's f at x here. X is an element of real numbers. This entire chapter is a good review for the course because we go over all your functions, domain, range, all kinds of stuff. So this is a good recap here. What's the domain of that parent function? That's a grade 11 parent function. Such that should be straight. Such that I'll fix that. Such that what? What's the domain of that function? No such that. That's just x is an element of real numbers, right? There's no restrictions on x for the parent function base 2 to the power of the x exponential function. I could sub in anything I want for x here, any decimal, any fraction, positive, negative, rational, irrational, doesn't matter. Whatever number I want, I could sub in there and I will be able to calculate it. So x is an element of real numbers. Okay, now let's look at g at x. What's the domain of g at x? Domain of g at x is what? So we spent a lot of time on rational functions here. Hopefully everyone's quick at this one. X is an element of real numbers. Do we have a such that this time? We do. Such that x cannot equal 4 because of the restrictions on the denominator. X cannot equal 4. So what's the domain of the whole thing? What's the domain of f at x and g at x? They're pretty much the same. The only restriction is we can't have, x can't be 4 here. So since they both have to have the same domain, I'm now going to have to say that for f plus g at x, it's going to be this one here because it's x is an element of real numbers, but x cannot equal 4. Even though x could be 4 here, that's fine. 2 to the power of 4, no problem, 16. But we can't have a 4 here, so we have to include that in our given domain. So the domain of f plus g at x is going to be x is an element of real numbers such that x cannot equal 4. We won't be able to add them together. Remember the one we just did up there? Let me just put it in black right here. This first one that I'm circling, A, we wouldn't be able to do that for the question that we just did because we have an f at 4, we can calculate an f at 4, but we can't calculate a g at 4, so we wouldn't be able to add the function like that or subtract it. So that's how we find the domain of two different functions. We won't be focusing too much on range. Most of the questions, you might have some in your homework that ask for domain and range, but really domain is what we're focusing on here. Example 1, we've got two polynomial functions here, and we want to graph them. So first of all, this is in factored form. That's going to be pretty straightforward to graph. This one is in standard form. They're both polynomial functions, so that means we're going to look at things like the degree and the leading coefficient, and it's a good review for going back to those earlier chapters, chapter 3, when we talked about polynomial functions. So you probably, as I said, you're going to run out of room on your page. There's not enough room here for this. We have a lot of little steps to do for part A. Let's start with for f at x. stating what we can tell just by looking at the equation. So f at x, what's its degree? We look at how many x's, we got 3 of them there. If we multiply them all together, it would be x to the power 3. So it's cubic. It's cubic. It's got zeros. So let me just do kind of a bullet list here. It's cubic. It's got zeros or x-intercepts. Where are they? Well, it's already factored. So zeros are at x equals -1, 2, and 4. What about the leading coefficient? The leading coefficient, so we look at this a value and then we check it to make sure there's no other, when we distribute it in, that there's nothing else to multiply it with, and there's not. So our leading coefficient is negative. So if we have a cubic with a leading coefficient that's negative, so cubics either look like this or they look like this, right? One is increasing, mostly increasing, one is mostly decreasing. Which one is this going to be? Well, it's got a leading coefficient, so it's going to look like the one on the right there. So we've got some information there. What else do we know about it? Let me look at the list we have here. So we've got, the question says we need to use intercepts. We've got that. Those are the zeros. The degree is a 3. Test points. We haven't done the test points yet. So test points are good for helping us make sure that we're turning the graph kind of in the right space and that we're above or below the x-axis as we should be. An easy one is always the y-intercept, f at 0. That's an important one to find. So what is f at 0? F at 0 is -16. So if we were in class, I would give everybody a bunch of coordinates and we would all work them out together, but we'll just do it here quickly. F at 1 is a nice one to know. It's a pretty easy one to figure out. F at 1 is -12. How about f at 3? Because that's in between these zeros here. F at 3 is 8. What about f at -2? So see what's going on the left end. That is a 48. So we've got some good test points there. So we've got a good idea of what this graph looks like. Before I graph it, since I have to put 2 on the same graph, I want to get an idea of what coordinates I have on the other one too. It'll help me set my scale if I do my groundwork first. So let's now look at g at x. G at x is going to require some more work. G at x is in standard form. Standard form is good for telling me the degree, which is a 3, leading coefficient, which is a +1, and y-intercept, which is an 8. But I can't tell where the zeros are. So to tell where the zeros are, I'm going to have to use the factor theorem. Plus or minus p over q, remember that? But my q is just a 1, so it's really just factors of 8. So I'm looking at plus or minus 1, plus or minus 2, plus or minus 4, and I keep subbing them in until I find one that works. So I hope you would try this, but I will tell you that g at -1 is equal to 0. That would be the first one you would find. Now what? Once you find one of them, how do we get factors out of that? That tells me that x plus 1 is a factor, but how do I finish factoring it? So you're going either to long division or synthetic division here. So this is something you can do on your own. I'm not going to do all the work here for you. You should be pretty good at this by now. And this is a good time to press pause and try it, because the next line you're going to see up here are all the factors. When you're done your factoring, whether you do long division or synthetic, whatever you get up here is going to have to be factored again. You're going to have a quadratic here. It's going to be an x squared up there. So you'll have to factor that again. So when you press pause and when you come back, I will show you what it looks like all factored. There we go, all factored. So that gives us the intercepts, or the zeros, intercepts when x equals -1, 2, and 4. And that's what we had last time too, so that's interesting. It's not the same function though, because they have different leading coefficients. This one, the leading coefficient is positive. So this one is going to have this kind of shape, right? it's going to be overall increasing. And its degree is 3 as well. Degree is 3, so it's cubic. Oops, wrong color of green there. Cubic. Still the wrong color of green. Cubic. Now let's get some test points. So the y-intercept, that one's easy because it's in standard form. The y-intercept is 8. What about, again, let's do f at 1. Oh, sorry, g. Sorry, g, not f. We already did f. G at 0 is 8. G at 1 is 6. G at 3. What's g at 3? That is a -4. So we get a few of these ones here. Yeah. So now we have enough to graph it. Well, I have to set up my scale first. When I look for my x and y axis scale, first look at your x numbers. Your x numbers are here and here. So I only have, the biggest number I have here is a 4. So I'm going to count by 0.5. So on my x-axis, I'm going to have my scale being increasing by 0.5, so I can spread it out a bit. Now, what about the y-axis? Okay, my biggest y value is right here, this 48. Just because I have that number does not mean I have to graph it. I do not have to graph -2, 48. That would be way up here somewhere, right? That doesn't, I don't have to adjust. All of my other numbers are much smaller than that, so I'm not going to count by, tens or something just so I can fit that point in. So I'm just not going to include that point because I don't want a scale that is so distorted that I really can't see my function. I want to be able to get most of the points in there. So to get most of the points in there, especially the y-intercepts, those are important ones to get. That's a -16. My f at 0 is -16, so I'm going to count by 2's here. So 2, 4. I'm only going to label every second one because it gets crowded. 6, 8, 10, 12, and so on. I'm going to start by graphing f at x, and I'm going to use purple for that. Let's put the zeros on there. I've got a 0 at -1, 2, and 4. I've got some other values. F at 0 is -16. F at 1 is 12. And F at -2 is 48. So that one I couldn't fit on. I'm going to put a little arrow up here just to remind myself that it should be going up there. That's where it should be. F at 3 is 8. Okay. And remember that it's cubic, so I know what the shape should look like. And I know that it should be, oops, f at 1 is -12, not +12. -12. So even as I was talking there, I said, oh, it's supposed to be cubic, and look at the shape. And as I was saying that, I looked at that one point and I thought, that's not right. So I just checked, and it is a -12. I misplaced it. We tend to want to, when we're graphing a cubic, so this cubic is going to be going in this direction, right? This is overall a decreasing cubic. So it's got to have that shape, which is good. I have my arrow up here, and that's right. That's where it's supposed to be. We tend to want to make our turning points whatever our highest or lowest point are. Now, I don't know that this is a local maximum. I can turn there if I want to. I don't have to. This is just a sketch, but I'm going to now try to connect my dots, and I'm actually going to, so when I go here, I'm going to curve above this a little bit just to show you we don't have to make it a turning point. It doesn't even, it looks like it probably should be, and that's supposed to be straight through there. These are all straight through x-intercepts. They don't bounce or anything. And then continue up here, and then obviously I'm going way up like that, but I'll just put an arrow. So there's my purple one, which is f at x. Now I want to graph g at x. So the points I have for g at x is the same intercepts, exactly the same intercepts. So this is in the same family of functions because they share the same intercepts. I have g at 0 is 8. G at 1 is 6, so those are looking good so far. G at 3 is -4. So these are looking like where they should be. I didn't get any other points on the other side of -1 because they got too big. So let's make a cubic out of these dots. So there we have G at x and f at x. Good review for graphing polynomial functions because we haven't done anything new yet. That factor theorem, the division we did, that's all old stuff. We haven't done anything new. So what we are going to do new is the next point, B, that we have to do. We have to graph h at x, which is f at x minus g at x. Now there's a couple of different ways to do it, but one way, the way we're going to do this one here, I'm going to draw a chart here. So I'm just going to draw a line across and a few lines down like this. So what I'm putting here, I'm putting my x values in here, and then since I'm doing f at x minus g at x, I'm going to put my x at x, f at x values there, g at x values here, and then my new one, h at x, is f at x minus g at x. Okay, so let's look at an x value of 0. What was f at 0? There it is right there. F at 0, that was a -16. What was g at 0? There it is. G at 0 was 8. So h at 0 is going to be -16 minus 8. That's going to be a -24. That means we're going to have the coordinates 0, -24. So here's where it's important that your test points kind of match so that you don't have to keep calculating. For example, I can do 1 when x is 1. So f at 1 was a -12. G at 1 was 6. So h at 1 is going to be -12 minus 6. That's -18. 1, -18 is another. Let's put these 2 points on. 0, -24. Oh, I can't really fit that on. 18, 20, 24. It would be about down here. 1, -18. That would be about here. So if I decided that I wanted to put a number in my chart, an x value that I don't have both, I would just calculate it. If I didn't calculate originally, let's say I wanted to do -1. I didn't calculate -1 for both of them, so I would just calculate them here and put them in. But do we have any more that are the same? Well, what we did find for both of them, for all of them, sorry, we will do -1. -1. F at -1, that was a 0. So F at -1 is 0. G at -1, that's also a 0. So H at -1 is also going to be a 0. That means the zeros that we had aren't going to move. They're going to be invariant because they're all the same. So I'm going to put red dots on all my x-intercepts because they're all staying at 0. Let's do a 3 here. 3, F at 3, we did that one. That's 8. G at 3 is -4. So H at 3 is 8 plus 4. That's a 12. So that's giving us the coordinate 3, 12. Let's put that on the graph. 3, 12. So what I was saying before is if you pick a number that we didn't calculate a test point for, such as 5, then you could just calculate them now if you wanted to. But 5 is going to be off our grid. I'm not going to put that one on there because it's not going to fit, but you could just calculate that later. So this is one way to get coordinates on a new function. So now we have to connect our dots, and it's going to be another cubic because we just have 2 cubics. And connect our dots and try to get a new graph out for h at x. So there's my rendition of h at x, and we want the domain of the function. Remember what I said about domain earlier, the domains have to overlap. So the domain of f at x, what was the domain of f at x? The domain of f at x was x is an element of real numbers because it's polynomial, and all polynomial functions have the domain x is an element of real numbers. So f at x and g at x both have that domain. X is an element of real numbers, which means h at x has the domain. H at x's domain is x is an element of real numbers, because its original two functions had no restrictions on them, and when we're adding them, that means that our new one won't have any as well, and that's because they're all polynomial functions. So that was a big question. It was a good review. We did a lot of review there. The only new thing in this question was really subtracting some coordinates to get some new ones. Example 2. F at x is an exponential, g at x is a cubic, and we want to get the equations of the functions when we add them and when we subtract them. It's pretty straightforward. It's actually easier when the functions don't match. Like our last polynomial function, they matched. We could actually have taken those cubics and actually added them together, collected like terms. It would have worked out just fine. But these, sorry, I should write plus here. F at x plus g at x. These aren't the same. These aren't even both polynomial functions. If they're both polynomial functions, it would be much easier to add. All I can do here is write out 3 to the power of x plus minus, I'm going to make that a minus, x cubed. I can't do anything further. I can't collect them. Those are they're unlike functions. That is the function of f at x plus g at x. So then what's the equation of f at x minus g at x? Same thing. 3 to the power of x, 3 to the power of x minus negative, so that becomes a plus, x cubed. That's it. That's all I can do with that. There's no more collecting I can do. Part B, the new functions were graphed using technology below. So that the first one here, f at x plus g at x, that's the first equation we have here. And the second equation, f at x minus g at x, is right here. Label the key coordinates on the graphs, fill in the chart and the characteristics. So the key coordinates that we need, when you look at the chart, especially this one here, is asking for intervals of increase and decrease. So to know what an interval of increase and decrease is, I need to know turning points. We're going to label, put dots on all about where we think the turning points are here. Let's do the addition, the sum first. So these ones are pretty hard to tell. I know what they are exactly, so we'll just write these down here. That coordinate there is negative 0.47, comma, 0.7. This one up at the top is 1.12 and 2.02. So these I'm getting from Desmos. Well, yeah, you guys would just be looking at the graph and kind of estimating what you think it is. And down here we have 2.77 and negative 0.28. Okay, those are important coordinates. What about on the bottom one? It looks like a cubic, that one there. So on that one, I'm just going to give you the x-intercept on this one here. And again, you would just look at it and say, well, I think it's about negative 0.7 or something. So it is negative 0.7, comma, actually 0.76, but that's okay, 0. That's the intercept. So those points we're going to need to fill in the chart. Let's start with symmetry. So I'm going to use green for f at x. F at x, I'm going to use green for that. What's the symmetry of that graph? Can you picture 3 to the power of x? I hope so. 3 to the power of x would be like this, right? Symmetry? None. There's no symmetry. That was messy. Clean that up. Proper word, of course, is neither. What about intervals of increase and decrease? Just on the green one that I've drawn here. So I'm not looking at the adding or subtracting functions yet. I'm just looking at the original parent function. It's always increasing, so it's increasing everywhere. How do we write that? We say that it's increasing from when x, so we only talk about x values, it's increasing from negative infinity to positive infinity. Lost my pen. Negative infinity to positive infinity. That's where it's increasing. It's increasing always, negative. How many zeros does it have? Well, look at it. None. It has an asymptote there. What about an absolute max or an absolute min? It doesn't. It's always increasing. It never, from infinity to positive infinity. So there's no max and there's no min. How about the domain? That's just x is an element of real numbers. How about the range? We haven't talked too much about the range, but when we're given a picture of a graph, for sure we can identify the range. The range is y is greater. Whoops, I should put brackets around that. I might run out of room here. Actually, I'm just going to do a short version here because I don't have room to draw the whole thing. Y is greater than 0. Y is an element of real numbers such that y is greater than 0. That's the range. The next one we want to do is the other parent function that we're talking about, which is negative x cubed up here. Negative x cubed. That's the second one we're going to do. What does negative x cubed look like? Negative x cubed is the cubic function, but decreasing, right? That's negative x cubed right there. What about its symmetry? Yes, it has odd symmetry. It's just like the parent function x cubed. It has odd symmetry, or you could think of it as rotational symmetry about the origin. What about increasing and decreasing? This one is always decreasing. So it's decreasing for x values of negative infinity to positive infinity. How many zeros? Well, as you know, if your exponent is odd, it has to cross once. Now, it could cross 3 times, but this one is only crossing once because it has, other than reflection, it has no stretch or compressions. Absolute max or min? Nope, none of those. No max, no min. Same as the one we just did. There's no max and there's no min. What's the domain? Again, it's a polynomial function. So the domain of any polynomial function is x is an element of real numbers. How about the range? Well, I can fit this one on because its range is also y is an element of real numbers. Now, what about f at x plus g at x? Okay, now is a good time for you to press pause and try to do this yourself. You're going to do the whole row for f at x plus g at x, and you have a graph to look at right here. So look at this graph and fill in the chart. I'm going to press pause too, and I'm going to fill in the whole chart, and when I'm done, you'll see all of the answers here. All right, how did you do? I'm going to go over a little bit before I skip ahead. There was neither symmetry. Now, the increasing decreasing was probably the most complicated. I started with listing the increasing. So this part here is decreasing, decreasing. So here's an increasing interval right here, this little piece. So it's increasing from when x is 0.47 until x is 1.22. Then it decreases again. But then we have another increasing interval that's from x equals 2.77 to infinity. So there's the 2 parts of the increasing, and similarly there's 2 sections where it's decreasing. It has 2 zeros right in here. There's 2 zeros. X is an element of real numbers, and you can tell that by, you may not know that by looking at the equation, right? That's a weird looking equation, but you've got a graph and you can see the arrows here. So we assume they go on to infinity. X is an element of real numbers, and the range is y is an element of real numbers such that, I just snap room, y is greater than or equal to, our lowest value here is negative 0.28, but our range is all higher than that. So try it again with your f at x minus g at x column in here. Fill all this in, press pause, do it yourself, and I will do it myself too. So there's our last, these answers go with this graph here. Neither symmetry, it's always increasing. There's 1 0, there's no max, there's no min. X is an element of real numbers and y is an element of real numbers. So there we have a lesson on adding and subtracting different functions. chart to see what they look like. Now we can't collect like terms when they're completely different functions, but when they are, we can. So do some practice questions, and on your handout there's some important notes at the bottom of your page, so please take a look at that.